In this video, we'll see how we can perform inference in the sparse coding model and compute the latent representation for a given input. So we've seen the objective in sparse coding. We're trying to find a dictionary matrix such that we can encode each of our training input into a representation which contains information about what was the original input and is also sparse. And so to compute this objective and also to optimize it, we need in the inner loop of this sum to actually be able to perform the minimization here. In other words, given an xt, we need to be able to encode our input into the sparse representation. So to find the sparse representation that optimizes the reconstruction error plus sparsity penalty objective. So in this video, we'll see an algorithm for doing that. So let's assume for now that we are given a dictionary matrix. Now we have to infer the latent representation, the sparse representation h of xt. So what we have to do is optimize this combination of a squared reconstruction term and a sparsity term on ht. We have to optimize that with respect to the latent representation. So we have to optimize the combination, the sum of a quadratic function with an L1 type function. Now, one thing we could do is gradient descent. We've used gradient descent algorithms before, so why not for this particular problem? And so we could initialize the latent representation to some value, compute the gradient with respect to the current value of the latent representation, and update it using the gradient information, so by going in the opposite direction of the gradient. So we see that the gradient has this term here, which comes from the reconstruction term, and a term here which we recognize from, with the sine function that we typically see when we have an L1 type function to optimize, when we're looking at the gradient of an L1 function. So we could perform gradient descent, updating the latent representation until it converges, and we found an optimal value for this. One thing that could be said about this particular problem is that because it's the sum of two convex functions, then the actual objective is convex. So unlike, say, training a neural network, this optimization problem has a unique global optima. And so in that sense, it's a fairly easy problem to optimize. Let's look at the gradient for a single hidden unit. So we have the gradient from, or the partial derivative from the squared reconstruction. So it's the difference between the reconstruction and the actual input, multiplied by the vector that corresponds to that hidden unit's weights with the input. So that hidden unit's atom or dictionary element. So you have this part, and then we have the sign here. Now we know that the L1 norm encourages values, in this case the hidden units, to be will force some of them to be exactly 0. Now if we do regular gradient descent, it's actually very unlikely that we'll do a gradient update and we'll fall exactly on an h value which is equal to 0. And just actually generally speaking, the L1 norm is not differentiable at 0. So in that sense, we can't really gradient descent is not properly defined for this objective, because we don't have the gradient at exactly 0, even though we actually expect that some of the hidden units should fall exactly on 0, because the L1 norm encourages sparsity. So a solution for this is to do the following. So I won't explain the rationale and theory behind why this is a good thing to do. I'll just give you an intuition for why this could work. So what we'll do is that we'll do something very close to gradient descent, and where we'll alternate between performing an update based on the gradient of reconstruction error and then performing an update based on the gradient of the L1, so based on this sign here. But what we'll do is that if the value of a hidden unit changes sign only because the L1 norm gradient is pushing it towards zeros, and because of the step size or learning rate we've been using, it's actually gone past zero, so it changes sign. Then if it changes sign, we'll actually clamp the latent representation unit or the hidden unit to exactly zero. And so intuitively, the idea here is that if it's the gradient from the sparsity term that is switching the sign, well, actually, the sparsity term, we know that it prefers everything to be zero. So presumably, it's trying to set it exactly at zero, so we'll do that. We'll set it exactly to zero if it changes sign. So that yields the following algorithm. So first, we update each hidden unit based on the gradient descent update rule for only the reconstruction. So we're taking the previous value, and then we're subtracting some step size or learning rate times the gradient of the reconstruction. And then we check whether the sign of the sign of the new value for the hidden unit is different from the sign of the same hidden unit, but after we would apply the gradient update based on the gradient for the L1 norm. So in other words, this is another way of writing, or this in words, this would correspond to checking whether HKT is changing sign. If it's changing sign, then we set it to zero. And otherwise, we just apply the regular update. So we just subtract alpha times lambda, which is the regularization or the sparsity weight, times the sign of H. Okay, so we're essentially shrinking H towards zero. And so we apply these updates for all hidden units, and then we repeat the procedure until the values of the hidden units doesn't change too much. So by defining some sort of convergence criteria. So this algorithm is known as ISTA, iterative shrinkage and threshold algorithm. So we have its version in the vector form. We initialize all the whole vector of sparse coding representation. For instance, we could initialize it to everything to zero. And then until the vector has converged, we update it based on the reconstruction error gradient. And then we apply this shrink function here. So the shrink function it does exactly what I said before. For each hidden unit, it looks at whether the update would make each hidden unit change sign. If it does, you clamp it to zero. Otherwise, you just shrink it towards zero. Okay. So the shrink function, I define it more formally here between A and B. So A would be the H here, and B would be this. It's actually a scalar. In this case, it's a scalar. It's a vector that consists of only this value. So what the shrink operation does is that it takes the absolute value of each element in the vector, subtracts it a value here, which is going to be positive. So this is always going to be positive. So it shrinks it towards zero. But now if by shrinking it, it actually becomes negative, we're taking the absolute value. So in other words, it's changing sign. Then we're going to set it to zero. So we're taking the max between this and zero. And then we multiply back by the sign because we had removed the sign of the element here. Okay. So visually, this is what the shrink function looks like. If the input of the shrink function, the part in A here, is smaller than BI, so which in this case, BI corresponded to 10. So BI would be this alpha times lambda here. If it's smaller than that value in absolute value, so it's within this interval, then the shrink is going to output exactly zero. And otherwise, it's going to grow linearly. So notice that once at 1.5, the output value is 0.5. So that's for BI equal to 1. So it shrank towards zero by subtracting 1. And if subtracting 1 would have changed the sign of the element, it just outputs 0 exactly. And now this algorithm is known to converge if 1 over the step size is bigger than the largest eigenvalue of this matrix here. So that's just a theoretical condition for for convergence. So in other words, if alpha, so if 1 over alpha is big enough, or in other words, if alpha is small enough, then this will converge. And this is a fairly popular algorithm for performing inference. So once we're done, the algorithm returns what we call h of xt. It returns the sparse representation for an input. And we notice that this, which is equivalent to encoding the input into a hidden layer, is much more complicated, is a fairly complicated iterative process, which is more complicated compared to in an autoencoder where we have a linear transform followed by nonlinearity. So in fact, what happens here is that the hidden units are sort of competing with each other to explain it. And they're competing because there's a sparsity terms that wants everything to be 0. And so effectively what's going to happen is the hidden units that best explain something in the input and explains it better than other hidden units are going to be non-zero. And the other things that are sort of overshadowed by other hidden units that are more appropriate for the input are going to be shrink to 0. So there's this sparse coding model. One property it has is that hidden units compete with each other for explaining the input. There are other improvements we can make. So for instance, ISTA updates all hidden units simultaneously, which might be wasteful because maybe some hidden units will converge faster than others. And so one idea is to update only the most promising hidden unit at every iteration. So we do less computation every iteration. I recommend you look at this paper here, which it actually mentions, so this paper doesn't propose this algorithm, but it describes it in fairly well. So it describes a coordinate descent algorithm for performing this inference problem, inferring the sparse codes. And one advantage it has is that it does not require a learning rate or a step size for like ISTA, which requires an alpha in updating the latent representation. So if you're interested, if you want a faster algorithm that also has the advantage of not requiring specifying a learning rate for doing inference, I suggest you look at this particular paper. All right, so that sums up what we had to say about how to infer sparse codes for a given input.